Of a function. Continuity of a function as an idea is not very difficult. Okay? A function is continuous basically in call it layman's terms, call it a non-technical definition. A function is continuous if you can draw it without lifting your writing device, okay? Pen or pencil, okay? The idea is very simple in these terms, okay? All right, so yeah, we've got a continuous function. If I can keep on drawing, blah, all right. Okay, that one's continuous, isn't it? I never lifted. Then this one, well, that one's not so much continuous. It's continuous until you get to, let's say that's 1, right? We're continuous until we get to 1, and then after 1, we are continuous. So there's a discontinuity, we would call it. It's discontinuous at 1. But it's continuous everywhere else, okay? All right, so that's the idea. I just want to make sure you got the idea at least in mind there. Everywhere else except 1, that one is. This one's continuous everywhere. This one is discontinuous at 1, continuous everywhere else. Okay, that's, like I said, that's the layman's definition. However, we can define this now actually using limits, believe it or not. The formal definition way of defining it. Because here's the thing. This one's continuous because at any point, say this is -3, at any point I can do this. I can say, well, the limit is coming in at -3 here, and that's the limit from the left and the limit from the right. So I've got a limit at -3 is that, and the function value actually also matches up. However, over here, what's the problem at 1? Well, what's the limit at 1? There isn't one. Okay? So that's one of the ways we can tell discontinuity. If you don't have a limit at a particular x value, it's not continuous there. There's some others. But that's kind of one example. There's some others. But the definition of continuity, here it is. A function f is continuous at a if the limit x approaches a of f of x equals the function value at a. So there's kind of 3 parts there. First of all, so we'll call this the 3-part continuity test. There's 3 parts to that. You've got the limit, x approaches a, exists. Number 2, the function value at a exists. And then number 3, the 2 are equal. That's what you got. So that's what we're going to do here is just kind of verify those 3 things on a couple of different functions. First of all, the first one is going to be on this handout right here. Pass one back there. All right, so let's take a look here on the handout. I've kind of already gone through that one with you, but more formally here. All right, so we've got a function graphed, and it's sort of like this. Whoops. Not so much far over, okay? All right, so this is 1, this is 4, this is 5, and it goes out to 7 right there. Okay. So the handout, that's what I got. All right, so number 1, easy question. Where is this one discontinuous? Is this continuous at 5? Any others? Yeah, it doesn't exist. Well, the function doesn't exist past 7. It looks like it does continue off the page there. So, yeah, so it's as far as discontinuous. So it's lifting your pencil, isn't it? Do I have to lift my pencil to go to this one? Yes, that's discontinuity right there. So you also got one at 1. If I keep going and keep going, do I have to lift my pencil to go to the next? Yeah. So at 4 also. So it's discontinuous at 5, 1, and at 4. Okay. Now, the trick then comes is, as number 1 states, explain then each answer using the definition of continuity. And they could all be very well different. I think a couple of these are different. So let's explain why at 5 it's discontinuous. So that's using either these 3 things or one of the 3, because for this to be continuous, all 3 have to be checked. If one of them's not, then it's discontinuous, you see. So at x equals 5, which one of these fails? Does the limit exist at 5? As a, of course, is the x value we're talking about. That's a. Does the limit exist at 5? No, the limit does not exist at 5 because you got limit from the left, limit from the right. They're different. So the limit, so that's it. The limit as x approaches 5 of my f of x does not exist. That's sufficient. And I guess we got technical about it. Well, that's really it. That's it. Yeah. Okay. All right. What's the explanation at 1? Why is it? Does the limit exist at 1? Yep. There's a limit at 1 because it's coming in here at 1. It's coming in here at 1. There's a limit there. So that does exist. The limit would be, looks like 5.5, but it does have a limit. What about the function value at 1? Is there a function value at 1? Nope. There's not a function value at 1. There's an open circle, so there's no function value at 1. Does not exist, undefined, however you want to put that. Okay? So that's last but not least, x is 4. At x is 4, we're coming into this one. All right, so we're coming in. Do we have a limit? Yep, from the left and right, we've got a limit, don't we? The limit's up here. It looks like it's about 7. So there is a limit, so that's checked. Is there a function value at 4? Yep. There's a function value at 4. It's right here. It's looks like 3. So that's checked. But what about that? Well, the limit, I should have written them down. The limit as x approaches 4 is 7. F of 4, though, is 3. So the two don't match. These aren't equal. That's your explanation. For it to be continuous, you have to have all 3. Limit exists, the function value exists, and they're equal. So since on number 4, the two aren't equal, that's why this continuous function, this function is discontinuous there. Okay? All right. Well, there's a second part to my question there, down at the bottom. Number 2 is, what domain intervals is the graph continuous? All right, here's the deal. All right, so we said it's discontinuous at 1 and 4, 5. So we kind of have to break it up that way. Continuous parts have to be open intervals. You know what I mean by that? Open intervals. That means not including the endpoints. So these will always be open, what are called open intervals, that don't include the endpoints. So we're not going to include endpoints. Various reasons for that, but and basically it gets down to, like here at 7, I can't say whether it's continuous or not at 7 because I don't know what happens to the graph here. It's just starting here at 7. I don't know what happens on the left, so there can't be a limit because the limit has to be from the, on the right. I don't know what happens on the right. So does the limit come in here from the right? I don't know. So that's kind of the idea, but they are open intervals. All right, so using that fact, and yeah, in this case, this does go off the page, so I can just say that it just continues on there. So it is continuous from negative infinity to where? All the way until we get to 1. And these also, these are domain intervals, so I'm talking about on the x-axis, from the x-axis standpoint. Okay, so it goes from negative infinity all the way to 1, continuous. I don't have to lift my pencil until I get to 1. So from negative infinity on the x to 1. That's the first domain interval where it's continuous. And these are open, so I'm not going to bracket those off. All right, but then where is it continuous from there? Well, it's continuous then from 1 to 4, isn't it? And again, don't include those endpoints, so parentheses those off. And then continuous until from 4 to 5. Again, I'm talking on the x-axis here. Here to here, so that's 4 to 5. So from negative infinity to 1, and then 1 to 4, and then 4 to 5, and then last but not least, from 5 to 7. And you'll see the union symbol between those, just saying put all those together. Okay? Okay on that. All right. Now, let's, so that was a function just from the graph. Let's say we just have a regular old function. Well, maybe it's not so regular, but say we have a function. And it's going to be f of x equals 3x plus 1 over x squared. And this is kind of approaching it from the other standpoint here. Use the definition of continuity. To verify that f is continuous at a equals 2. So how would I do that? Well, that's the 3-part checklist. Part number 1, what is the limit as x approaches a, which is 2 here, of my f of x? Well, is there any problem with substituting to get the limit? It's just the limit as x approaches 2 of 3x plus 1 over x squared. Is there any reason not to just substitute there? Not one reason at all. Okay. So I just substitute, so I get 3 times 2 plus 1 over 2 squared. 6 plus a fourth, that's 6 1/4. That's my limit. Part 2 then, what is the function value at a, which is the function value at 2? Well, it's 3 times 2 plus 1 over 2 squared, which is 6 1/4, what we just did. And then part 3, what about the limit as x approaches 2 of f of x compared to the f of 2? Is it equal? Yes. Check, check, check. Okay, that's it. Okay, so just writing those 3 parts down, that's basically all there is to that one if it asks that way. Okay, now let's go back to another one here. Where is the function discontinuous? And explain. All right. What if I have f of x, number 1, f of x equals 1 over x? Well, you know, you can utilize what you know about that. You can graph it, look at it that way, whatever. Okay. Where would you look even? Well, if we look at the graph, what does the graph look like? 1 over x? Like that? Something? Where's the discontinuous? At 0. Why? And again, we're going to use the definition of continuity. How would you explain that using these 3 parts? What doesn't exist here? There's 2 things. Both of those things don't exist, do they? Does the limit exist at 0? The limit as x approaches 0 of my f of x does not exist. And neither does f at 0 exist, does it? So both of those facts, yeah, it's discontinuous at 0 because of those 2 facts. The limit doesn't exist. You got one going to negative infinity, you got the other going to positive infinity on the right and left side. Then the function value, yeah, you can't even plug in x to be 0. So for it to be continuous, you have to be able to plug in your value. Okay. Let me mention this one. I'm going to do it. Run low. Okay. A couple more real quick here. The greatest integer, we just talked about that one. It's the one with the steps, but I was going to mention that here because this one has a whole bunch of discontinuities, doesn't it? You start here at 0, and then it jumps at 1, and then it jumps at 2. So where is that? Whoops, a little closer. Where's the discontinuities? Well, there's a bunch of them. You can say it in different ways. Where is it discontinuous? It's discontinuous at, well, it's discontinuous at 0, at 1, at 2, 3, 4, negative 1, negative 2. So you can do that sort of thing. Or you could say at x is an integer. At any integer, it does not exist. I mean, it is discontinuous. And why? Well, at each integer, it doesn't have a limit, right? Something like that. I did want to mention one more, real quick, like here. Number 3. F of x equals x minus 2 over x squared minus 4. Where is that one discontinuous? Well, if you look here, the graph is a little bit deceptive. X minus 2, x minus 2 divided by x squared minus 4. Because, yeah, here's what you get. And then here, but a little deceptive because actually there's a hole in the graph at 2. And we've looked at this one before, but x can't be 2, right? Because the bottom would be 0, so you know something's going on at 2. And then at negative 2, of course, you got the asymptote there. But all right, so where's this one discontinuous? 2 and negative 2. Now, why in each case is it discontinuous? It's actually, well, slightly different reasons. At x equals 2, why is it discontinuous? What part fails? Does the limit exist? Yeah. I've got a limit at x equals 2, right? It's coming in here, it's coming in here. I've got a limit at x equals 2, but what don't I have? The function value at 2. The function value at 2 does not exist. What about at negative 2? Does the limit exist? The limit does not exist there, and the function value doesn't exist either. But okay? So, anyway.